Throw another log on the fire. Cook me up some bacon and some bacon. Oh, wait, hold a second. We're not talking about that kind of log. We're actually talking about logarithmic. And we're actually talking about logarithmic functions. Yeah, sure, we'll call them logs. Why not? But a logarithmic function is completely different than throwing something on a fire and cooking up bacon and beans, baby. I'll tell you that right now. But surprisingly enough, what you don't know about logarithms is this. You've actually done kind of the precursor to logarithms when we did exponential functions. Huh? Surprisingly, a logarithmic function is an inverse of an exponential. So basically, all you're going to do is going to be flipping x's and y's all the time. Holy moly, that sounds like fun. I know, isn't it? Okay, so let's get into it. It says, for example, do you remember this? Do you remember this guy? There's a nice exponential function for you. And we always had problems solving something like this. We ended up going, oh, we're going to take this one and we're going to put it into y1 in my graphing calculator. And I'm going to put that into my y2 in my graphing calculator. And I'm going to find some sort of intersect. This is going to go like this, up like this, and there's 10. I'm going to find that intersect. I'm going to go and do this. Oh, my goodness. What a pain in the butt, because you're suddenly graphing. You got to change this and that. You got to change your window settings. You got to go second calculate. Oh, way too much of a problem. There is a way to do this algebraically, and that's what this unit is all about. We're going to be playing around with that like crazy. Now, how do we do this? Real simple. We got to figure out a way somehow of isolating the x. That's where logarithms come in. Remember, I said a logarithm is the inverse of, you got it, the inverse of an exponential function. Okay, so we're going to use this idea of logarithms. What's an inverse? Real simple. Here's an exponential function right there. Y equals to the c to the power of x. Remember what an inverse means. An inverse means all you got to do is flip those two and you've got the inverse. It's that simple. It's really, really that simple. Okay? So a logarithmic function can be written in exponential form like this. And you got to recognize that as an inverse of our exponential form. So how do we technically talk about this? How do we say things about it? Well, technically, we refer to it as this. When we do the inverse, we write it as log base c of x. Well, wait, what? What did I just say? I just said base. Well, think about it. When we're talking exponents, is that guy and that guy not the base of your exponent? Of course it is. Now, look at a logarithm. A logarithm then has the base written right there. That, in fact, is the base of the logarithm. Oh my gotcha. Huh. Well, okay, so I'm okay with this. I don't know about you. Let's go play a little bit here and let's learn some stuff. Okay, slow down, slow down. We got to get through the technical stuff first. Okay, so logarithmic function, bada bum, looks like this guy, right? But there's some key factors that you need to know. First things first, all of those bases, yep, every single one of those bases has to be greater than 0, and the base cannot equal to 1. Do you remember in exponential functions when we let the base equal to 1? So we had something like y equals 1 to the power of x. Nothing really happened, right? Well, same thing goes with logarithmic functions. If you let that base equal to 1, not going to happen. Nothing's going to happen. It's going to be ugly. Okay. The other thing is we're going to let that base has to be greater than 0 when you're doing a log. That's kind of an interesting and important thing. We'll talk about that later on as to why. Okay. Don't forget that a logarithm, you can do this here and just exchange the x with the y and everything's good. But here's another important thing, something called a common logarithm. Well, the cool thing is if you look on your calculator, you're actually going to have a button here that says log, just like that. Don't believe me? Let me show you. Look, it's right there. Log. Now, when you hit the log button, and go ahead, grab your calculator and hit the log button. you're going to see it pop up as log. But I know what you're saying. Well, what's the base then? Shouldn't there be a base written in there? When you hit log in your calculator, it's known as a common logarithm. And a common logarithm will have a base of 10 automatically. That's what makes a common logarithm a common logarithm. Okay, so base of 10. Okay, so let's go back to here. So common logarithm will always have a base 10. So when you hit log on your calculator, it's going to go log base 10, and then you can punch in whatever number you want. Got it? So far, so good, right? Okay, couple more things that we got to learn here before we go into some heavy-duty logarithms yet. Boom, let's go. To find the inverse of an exponential function, take the following steps. Switch the x's and y's, solve the y for using logarithms. Wait a second, how do I do that? Okay, well, simple. Watch, it's so incredibly easy, you're just going to freak out. First things first, if you get a y equals to some sort of base to the power of x, switch the x's and y's. Okay, x equals to c to the y. Now, what's cool here is this. That's the base of the logarithm. So you're just going to go log base c, okay? Now, the other thing that you have to remember here is this. You're going to want to solve for this x. So let this be equal to x. That's going to be your new y. That's how it works. It's that simple, folks. Right? Now, I know what you're saying. I don't get it. Well, can I show you something? Watch. Do you see this? Do you see this? Right? How do I get to that? Well, remember, this is a base, right? This is the way I do it. Base raised to the power of y is x. Base raised to the power of y is your x. That's it. It's kind of a, flip around things. Now, how are you going to remember this? You know what? If you just draw an arrow from here to here, like this, look at that. Tell me you've never seen that on your calculator before, which means, guess what? That means raised to the power of, right? Look on your calculator, right here. Look at your calculator. There's the button I'm talking about. That's the button I'm talking about. That button here, you hit it, means raised to the power of. So here, watch. I'm going to clear everything. I'm going to clear this 10 out of here so it doesn't distract us either. Hit that button, raised to the power of. Oh my God, yeah. That's a beautiful way to remember this. So if you actually go base raised to the power of y, look at that. Base raised to the power of y is this x. Huh? Well, there you go. Now, there are a couple more things we got to talk about before we go crazy here. All right? Some technical stuff. So if I give you a log that looks like this, right? You know and I know you can take that base, raise it to the power of y, base raised to the power of y equals x. So there it is in exponential form. Easy peasy, lemon squeezy. Now, there's some key words though. Yes, remember we talked about this b being the base of the logarithm. And we had some conditions with that. We said that that base has to be greater than 0 and the base cannot equal to 1. Do you remember, or I should say not equal to 1, not 0. Okay? Not equal to 1. Do you remember that exponential thing that we talked about earlier? How we can't have something like, there's your base, which is 2 to the x. We can have something like that. But what happens if your base is 1 to the power of x? Nothing. They're always going to give you the answer of 1. That's one of the reasons why, same thing with logarithms, you can't have this equal to a 1. Now, this x value inside the log is actually called the argument of the logarithm. And then once you've done this whole thing and evaluated it, we got a value of the logarithm, which is our answer. So a couple other things that we have to put in here as well. The argument, the value of this x here, cannot be negative either. Now, you're probably saying, whoa, there are so many conditions here that I have to memorize. Yep, you just said a mouthful. You got to go out and memorize it. I'm sorry. That's the only way you can do this. Okay? So stop this podcast, back up and watch this section again so that you can learn what those values actually are and you remember them. Okay? Okay. Now, I'm going to tell you why things like our argument here cannot be negative in a second. So in other words, my x's can't be negative. You know how we do it? Real simple. Let's look at a practical example. Do you remember this guy? We did this guy in the exponential section. Yes, the unit just before this, that was like our go-to exponential function. Y equals to 2 to the power of x. So I want to show you and I want to compare graphs. This idea of visuals is going to help us out huge. Do you remember how to graph this thing? Table of values was easy. Always start at the 0. 2 to the power of 0. Yeah, you know that. It's 1. 2 to the power of 1. 2. 2 to the power of 2. 4. 2 to the power of 3. 8 down here. Now, do you remember the rest? When you've got the negative 1, that means 2 to the power of negative 1 means flip it, you got a half. Flip it, you got a quarter. Flip it, you got an eighth. Remember how these guys were connected? Remember how those guys were connected? Do you remember? Go back and watch that podcast again if you can't remember that, but you should by now. Okay, now, remember what I said about a logarithm then? A logarithm then is simply the inverse. So I've got my x here and I got my log here. So just inverse them. Notice I've got all the values here already. See? See how those x's become y's? Then the y's become x's. This is 1/8. This is 1/4. This is 1/2. This is 1. This is 2. This is 4. This is 8. That's simple. Okay? So let's do this particular graph in green. And let's remind ourselves what that graph looks like. Starting at 0, 0, 1, 1, 2, 2, 4, 3, 8, 5, 6, 7, 8. Then we go -1 is a half. -2 was a quarter. -3 was an 8. And you know and I know gets really, really close to this axis but never touches. Then the bend starts here and then it goes kaboom right off the graph, right? Now, take a look. I'm going to do the logarithm now in blue. Take a look at this guy and start plotting these values. Now we're looking at x's that are getting smaller. It's starting at 1, half, a quarter, an eighth. Oh my goodness. The next one is going to be a 16th and it's going to get smaller and smaller. But wait a second. Does the x actually become 0 ever? No. Neat. That's why we said earlier in the slide just before this, let's look at the slide just before this, we said I believe it was way down here, that the argument can never be negative. Now you know why. Because look at this. The reason why is because this x has, yep, you guessed it, a vertical asymptote. And the vertical asymptote is this axis, meaning that the base, or I should say the argument, can get close to 0, but is never 0, and it's never going to be negative. Wow. Okay, we'll get into that in a second. Here we go. Let's start plotting. 1, 0. So 1, 0. So now look at this. We got a point right there. 2, 1 right here, right? 4, 2, which is right here. And then the next one would be 8, which would be way out here somewhere, and that would be 3. But now look what happens when we go and we look at this guy. We got a half, -1, which is here. We got a quarter, -2. There's a quarter, -2. We got an eighth, -3. So you can see that this guy starts to hug this graph here, hug that axis, and then it starts to bend out that way and go in that direction there. Neato, neato, neato. And remember what I said, that these are inverses of each other. Well, I know what you're thinking. If they're inverses of each other, shouldn't they be reflected over y equals x? Oh, I wonder. There's 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, blah, 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 -1, 1, -2, 2, negative. I wonder. Okay, here we go. Let's draw our line. And look at this. There's our y equals to x. and you've got a perfect reflection of the green line, which is our exponential function, over your mirror, which is y equals to x, to your blue function, and oh my God, yeah, it works. So one or two things we still have to kind of put down here, and I'm sorry that this podcast is going a little long, but watch this. Let's go to this. Almost gave you the answers on that one. Do you remember the domain of the exponential functions? X can be anything it wants, right? How about the range, though? Well, if you can't figure out the range, go back and take a look at the graph. Look at the green graph. There's our exponential function. You realize that we have a horizontal asymptote. So that means our y values have to be greater than 0. Okay, so let's put that in. Our range has to be y greater than 0. And we can go down here and put in our equation of our asymptote. Our asymptote, of course, being y equals to 0 because this is a horizontal. Right? What's our x-intercept? Well, go back to the graph. Our x-intercept, do you remember? There is no x-intercept. This goes through that point. There's our y-intercept, but we have no x-intercept. So guess what? Our x-intercept does not exist. Our y-intercept, we know anything to the point of 0 is always going to give us 1. Now, this is the coolest part. You ready for this? Since this is an inverse, can't we just inverse everything of our exponential function? Yeah. So check this out. Domain. You know and I know, looking back here at the domain, it hugs this line. There's our 1, hugs this line, goes through it, and goes out this way. So any value greater than 0, which looks like this. Look, any value of x greater than 0. Does that not look familiar? Neat. How about our range? Well, it goes, if you go back here, it goes from way down in the negative to keeps on going out to the positives, and it's increasing. So in fact, okay, so we can say that our range is y as an element of R. X-intercept. Saw it. I even put an extra dot on it. Now I'm circling it. Our x-intercept, of course, is at 1. So this is a 1. Y-intercept does not exist. Remember, it approaches the y but doesn't touch it. Equation of our asymptote then. This too is flipped and becomes a vertical asymptote. Isn't that neat how these two are inverses of each other? So two functions are inverses of each other. The graphs of the exponential function and the inverse logarithmic functions are reflected over that y equals x. A lot to know, a lot to learn. Go watch this one again.